Good morning. I'd like to introduce Professor Moseley at University of Dundee. Thank you, Professor.
Thank you for that enthusiastic response. I could dance if you prefer. This is going to be quite a different talk from anything else you're going to hear, because I'm not really going to talk about biophotonics. And I thought it was quite useful to do this. I think this is the same one I used last week, so it was clean then. Be okay. No, it's okay. I just think it would be quite useful to talk about a related subject, because I want us to kind of broaden our horizon slightly and look outwards rather than inwards. We get involved in various kinds of work which has got quite a lot of immediate impact. Now, everybody who does work in a university or hospital has impact in what they do. But some of this work has got big political impact, social impact, and a kind of immediate clinical impact. And that's very good for motivation. It gets you up in the morning, it gets you really keen and enthusiastic, and you want to do your work because you know what you're doing is going to count, and it's going to count very quickly. This subject here, it's got two key elements which may surprise you. One is this business of energy efficient lighting, and I'll talk a little bit about that. This other thing is photosensitive individuals. You may think I'm talking about patients who are taking photofrin or PP9. I'm not actually talking about them. I'm talking about a different group of patients that you've possibly not come across, and hopefully this will get a little bit clearer as I talk. Let's face it, something has to get clearer. Now, let's get on to the background of this. We're looking at, well, because this was a talk based initially in our European experience, there is European legislation, which includes Britain. Despite what some people think, Britain is actually part of Europe. Although we're a separate island, we're still on the continent. The continent of Britain hasn't been invented yet, but it might come soon. And because of the legislation, we have to reduce our emissions of CO2, nitrous oxides, SO2s, and methane and all these nasty things. So we want to keep the lights on, but we don't want to put the nasty stuff out. So we have to get reduced energy consumption so that we get, to what's the polite expression, more lumens for our watt. So that's basically what's driving all this. And in fact, I was in São Paulo yesterday talking to a friend of mine, and they have car exhaust emission legislation in São Paulo, which I think is the only place in Brazil. So if you register your car outside, you're okay. Or if you drive outside, but within the city, there is an effort to keep down on pollution. So that's what's behind all this. It's a big, big international political subject. Now, the main player is this thing called the compact fluorescent lamp, CFL. And although there may be other more efficient light sources about to hit us, right now that is really the only big player that's out there. Basically, it's a fluorescent lamp. It's the same as the things that we've got up in the ceiling here, these long tubes, but they found a way to make it so that it's little and tight and curly, but it's still a fluorescent lamp. So you have all this underlying technology. Basically, in the fluorescent lamp, you have mercury. The mercury is heated up, it becomes a vapor, and it's excited by the electric current which goes through the mercury, and it actually produces UV radiation at particular lines. One of the strongest lines is 254 nanometers, and then that hits the phosphor coating and produces whatever light the phosphor is designed to produce. So that's basically how it works, just like any other fluorescent lamp. And you're probably familiar with those things now. When certainly in UK, if we go down to the hardware store, we can only buy fluorescent lamps. The old-fashioned tungsten filament incandescent lamp is no longer. It doesn't exist. It's dead. And we are now got these things. There are two basic designs of those. From our point of view, we describe them as single envelope or double envelope. The single envelope, you can actually see that it's a little curly-whirly fluorescent lamp. Some of them go round the way and others go up and down the way. The others are double envelope. And you can actually see the curly-whirly bits inside there, but there's a second envelope round about, and that's essentially for aesthetic reasons, so that when you take out your old incandescent lamp, you put one of those in, it looks much the same, and the light is kind of scattered around much the same, and it's a bit prettier than those. And that's the reason that the double envelope is produced. There are, of course, problems with CFLs. They do contain mercury, and there's various rules and regulations about how you get rid of your CFLs, which most people ignore. And of course, there's a query about UV radiation emissions. Are these things safe or not? And that's really when were brought into it. This was the first report, this committee on emerging and newly identified health risks. I was asked if I would join this committee to produce a report on CFLs in 2008. And I was told that the European Commission is about to introduce this new legislation. We're just a little bit concerned there could be health risks. And we said, yep, okay, when do you want your report? They said 4 weeks. And we said, that can't be done. So it took us 6 months to produce the report, which isn't bad going. It was one of these things because it was a strong political driver. All the governments, all the politicians wanted to say, we're introducing these new energy efficient lamps. We're going to make the world environmentally friendly, and that will help me to get re-elected. But nobody had actually thought about possible health effects. And suddenly there's a group of patients, these photosensitive patients, and I'm going to mention one or two of them as I go along, who got very, very concerned about this because they had experience of some of these fluorescent lamps which caused problems for them, and yet they knew the incandescent lamps, they knew and trusted them, and they knew they were okay. So they were very nervous about these new lamps, and nobody had actually looked into the health effects. It's true, if you look at the world literature, there was nothing, apart from scare stories, there was a lot in the media, but nothing in peer-reviewed literature about health effects as the world was about to change their light source. Impact on the environment, yeah, I don't know about that. Impact on human health, wow, this is a big step to take without even thinking about it. So we produced our report in 2008. We recommended the use of double envelope CFLs because of those highly sensitive individuals. I mean, there's a lot of crazy people out there who tell me they react to lighting, and they come for testing, and we try different lamps on their backs, and we can't see anything, and they're telling us we walk down a corridor and we know which lamps are on. Yeah, good, fine, okay, but we can't find it. But there are some people who do react, and I'm going to show you the results soon to those lamps. We were invited, if that's the right word, to redo our report 3 years later. We had upset I don't want to use a phrase lunatic fringe. We'd upset the crazies because they felt they were being ignored. We'd upset the lighting industry because they didn't want to change. So I guess we must have got something right. We upset everybody. So that must have been we're pretty well down the middle. So we were invited to come back, and this time not just do CFLs, but all sorts of lighting. So immediately we said, right, we're only doing electrical lighting, so let's rule out candles, etc. So that was a good start. But we had to look at LEDs now as they were beginning to appear. So that's all the background. Eventually I'm going to start talking and maybe tell you something interesting. What we wanted to do was look at the amount of UV coming from these CFLs and see whether that could exacerbate photodermatosis. That's skin conditions which are either caused by UV or visible light or made worse, exacerbated by UV or visible light exposure. And we see these patients, we're a referral unit for these patients that come for investigation, so we can test the patients and see whether that could be the case. We wanted to examine the spectral emission. There was very, very little information out there. We want to look at different makes and models and compare this single versus double envelope type of CFL. as far as I know, we are still the only group that have done actual patient studies. And the study I'm going to report here is the biggest, therefore, series that's ever been done, since the only other one we did ourselves, which was a pilot study. As I mentioned the other day, we've got in the fortunate position we have a calibration laboratory which is UCAS accredited, which means it's got an international certificate to say we can do calibrations, and we're inspected regularly to make sure that our calibrations are absolutely bang on. So we can measure a lot of lamps, and we could also test our volunteers. And this is how we tested our volunteers. We wrapped their arms up in light tight fabric, and we had little windows that we opened at different times. And we also, one of the windows, we put Dermagard, which is a UV protective film, just to let the visible light through, and that's all. Now, you can obviously see from a physicist's point of view that there are weaknesses in this setup. The dissymmetry is tricky when you're so close to a large source, and also the radiation cannot possibly be uniform. It was as good as we could do it. It's the real world. It's not the world of high precision physics, but that's really as good as you could do. Now, something else I want to mention, the distance away. We standardized on 5 centimeters. One of the reasons that the lighting industry don't pick up any of this stuff is that the standard for lighting is at 30 centimeters, which is quite reasonable for general room lighting. 30 centimeters is perfectly reasonable, or 500 lux if it's a big source for covering a large area. So 5 centimeters, we are going much closer. The lighting, we met with the lighting industry in Europe. They didn't for 1 minute query us going down to 5 centimeters. And our argument here was, because these lamps can go into an ordinary incandescent fitting rather than put up in the ceiling, then they could be close to the skin. So there could be a reading lamp. So you could be a photosensitive patient reading a book, maybe a little bit short-sighted, and the lamp's quite close to your skin. Or you're doing some task work which needs good lighting. Maybe you're doing some needlework or soldering, I don't know, whatever people do with their hands, and they need lighting. So it could be that in those sort of situations, the light could be close. And so we chose 5 centimeters, and that was never challenged. We thought that could have been a problem. So we tested photosensitive patients, and we also got some healthy volunteers. We have a database of healthy volunteers that we call up, and for a small fee, they just sit back and we expose their skin to UV. This is actually the number of lamps that we looked at. We had a master's student who worked very, very hard. The data here is from Leona, which she collected. It's amazing. 106 single envelope CFLs, 17 different models, 6 manufacturers over that sort of wattage. The Lighting Federation presented us, we asked them if they would give us contact lamp manufacturers, who then sent us boxes of lamps. We also went down to the local hardware stores so that we could buy our own lamps. And so between the two, we had a large number of lamps. There was no difference between the ones that were sent to us and the ones that we bought. We just thought, well, maybe they'll send us the special good ones. It didn't make any difference. I just want to show you some of the results. And one of the strange things when you work in these European committees, you meet European commissioners who tell you what the rules are, and they therefore extrapolate from the rules to reality. So they tell us there is no UV from these lamps. Okay, right, let's have a look at this. This is UVC, right? We're not even talking long wave UV. This is way down. This is wavelengths that the human population is not normally exposed to. And that's one thing to just take on board. We're now exposing people to a wavelength that there is no basis throughout evolutionary history for believing that we've ever been exposed to this wavelength. So we can measure UVC quite significantly at 5 centimeters from a number of sources. 2 different wavelengths. 254 is generally the more dominant one, and there's a 265 I don't see 265. Oh, is that 26? No, it's not. I think what Leona was saying was you get UVC at both of these wavelengths, so she's showing us the 254. You're going to tell me now, oh, one's at 253 and the other's 254. It's actually 253.7, and we measure at 1 nanometer intervals, so don't let's get too fussy about it. We call it 254. And then UVB. UVB runs from 280 up to 315 nanometers. And there's quite a lot of stuff coming out in UVB from different lamps. That's 10 something milliwatts per meter squared per nanometer, and that's 7 of them. I'll put that in some kind of context in a minute or two. But what I want you to know at the moment is that it's quite measurable at these wavelengths. Coming up to UVA, there's 334, getting quite a lot now, and then 365. And again, the 365 is actually a kind of bit of a mess, 365, 366. It's not a single clean line at that wavelength. So some of the lamps are producing quite a lot of UVA, and we've got a bit of UVB and a bit of UVC, none of which appears in any of the standards. All of these lamps would meet the standards because we've checked it according to the standards. That's the single envelope lamps. Stop me at any point if you want to. If you think, Harry, this is rubbish, just say so. You know, don't be polite. You know me well enough. You know, just say, I disagree with you. You're talking nonsense here. Go on, give us a laugh. You don't want to challenge me on any of this, or just talk about something? No, you're okay. You're all happy. Right, double envelope CFLs. Are they any better? Well, we get 65 of those from those different models and manufacturers. And you probably don't remember the numbers, but we're well down. We can still get a little bit of the UVC, although actually that's UVB, I beg your pardon. No UVC, so that's good. A little bit of UVB, and some of them get a bit of UVA, but the numbers are all much lower. Are generally much lower than the single envelope lamps. So this is our first point that we had to establish. This previous advice that we said single envelopes are better than double envelopes. Can we actually substantiate that on a big series of measurements? Previously we'd done about 20, now we're up to about 200. Yep, most of the double envelopes gave a much lower output than the single envelope. If I just start up here, because that's the thing you're going to look at, that's what catches the eye. These are some of our single envelope CFLs, and that was the highest of our double envelope CFLs. So in other words, you can get the occasional double envelope CFL, which will be higher than a single envelope CFL. That's not to say when you put an envelope round it, you get extra light out. It's just that different manufacturers have got different quality standards. The problem with the lamps is that because they're twisting their borosilicate glass very tightly, then the phosphor coating isn't always of the best quality. So you get some of the mercury lines shooting through. And that's the reason why you get the UV emissions from these lamps. So you will get the occasional double envelope CFL, which isn't good. But on the whole, if you look at the mean comparison of all these, UVC, we're talking about 2 milliwatts compared to 0.02 from the double envelope. UVB 99 versus 4. UVA2 is 315 to 340 nanometers. 81 versus 11. UVA1, which is the longer end of the UVA spectrum, not such a big difference, a factor of 2 here. So there is absolutely no doubt at all. In terms of your chances of being exposed to UV, double envelope much reduces your risk compared to single envelope. Now we have patients who are coming through our unit and we're testing them, and we have to be able to give them some clear advice. We show them the lamps so that they know what they're looking at, and we say your chances are much better to use a double envelope than a single envelope. But we do emphasize that we can't say definitely that every lamp will follow that. One of the things that we wondered about was batch-to-batch variation. Within batch variation. I think that's what this is, within batch. And we thought if we get one box of, well, that's got 8. I don't know what happened to the other 2. I think we broke them because we wanted to look at the coatings. So if we get one box of lamps, will they all be the same? In actual fact, they're not. One box of lamps, look at this one here. The luminance, which is the light coming out, was much of a muchness. The UVA1 and this one, much of a muchness. UVA2, yeah, it's got a little bit higher. UVB, UVC. You can see here, this particular lamp outshone its competitors within the same batch. I guess the quality control is not that tight. And when you look at the actual standards that these lamps have to comply with, they all comply. They don't have to meet this very rigorous standard that we're looking at here because we were interested in our photosensitive patients. So, are there alternatives to CFLs before I show you the clinical data? There are energy-efficient halogen lamps coming along. These are still basically tungsten lamps within a halogen environment, and they're actually more efficient than the previous halogen lamps that you would have bought 5 or 10 years ago, so that they do produce more light per watt than the old lamps, but in actual fact they're not as good as CFLs. And this is the sort of spectrum. It's like the black body spectrum that you get from the tungsten. And you can see in terms of UV, total UV, quite a variation, but that is a spot lamp. So in terms of the watts per lux, that's not really a problem to anybody. That's not going to be 5 centimeters from anyone. In fact, none of them is going to be 5 centimeters from anyone. Now, I don't expect you to immediately give me the answer, although possibly you could. Why do you think it was reasonable for us to put a CFL 5 centimeters from the skin, but not reasonable to put one of those lamps 5 centimeters from the skin? Give me a thought that you may have. Why would that be a silly thing? Why would nobody ever do it? Oh, you know the answer. No, you'll know the answer as well. Who? Oh, somebody there. No, what? Yeah, at the back. Okay, that's a very good answer. The use is different. They're intended for things like car headlamps. And if you're 5 centimeters from a car headlamp, the last thing you're going to worry about is how bright the UV is just before the car hits you. That's a good answer. It's not the answer I'm looking for. You always find that, the answer, the right answer is the one I'm looking for, but it is a good answer nonetheless. Yeah, another one.
Maybe halogen lamps are getting warm when...
Yeah, that's the answer I was looking for. So, yeah, good answer. That's it. I like that answer. It's black body. It's very hot. If you put that within 5 centimeters, it's going to be so hot you're going to jump away. So we didn't test this at 5 centimeters in patients or in volunteers because it was too hot. But we did, I think, I need to have Leona here to clarify exactly. I think these measurements were made at 5 centimeters. Yeah, it says it there, 5 centimeters. But in actual fact, when we go to test them in patients, you have to be 30 centimeters away, and then the problem disappears. Okay, what about LEDs? Everybody was telling us, LEDs, they're replacing CFLs, all this stuff. Yeah, okay, well, yeah, they may do. It's just as a little aside, we got a new kitchen built onto our house, and the electrician was very, very keen on LEDs. We had 6 in this little ceiling, and he said, right, we'll put some LEDs up. I said, I'm not sure about that. I'll give you some other. And I wanted all sorts of lighting. He said, well, look, why don't you put up different lights? And don't tell us what they are, and my wife and I will decide which one we like. My wife will decide, and I will agree which one we like. So we had a look, and we said, right, we like this one, but not that one. And he was so upset we didn't like the LEDs, because they were kind of bluish. Whereas we liked, it was energy-efficient halogens, which are still a kind of warm light. So they're coming along, but they're not quite there yet. And I'll show you a spectrum, and I'll explain why they're bluish. So that's basically your LEDs. Right, this is that's looking at the UV, And there's obviously next to no UV, basically. Anything below 400 is UV, so that's just almost visible. This is the reason, if you look at that sort of spectrum, the LEDs look bluish, because basically the LED, the ones which are used commercially, use a violet LED, which then impinges on the phosphor. So the phosphor then produces the longer wavelength light, and basically it depends on the balance between this LED peak and the phosphor, what the light looks like. And certainly the early LEDs had very high peaks here and not very much in the phosphor. So the LEDs which are warm light are the ones where they've got more from their phosphor and less of the LED coming through. But they tend to be less efficient, which is rather paradoxical. So the LEDs aren't quite there yet, although I'm sure they'll be on their way, and probably as I speak, they've now got an LED which beats the pants off anything else. This was just to look at the different kinds of lamps and the different kinds of emissions, just to put them on a plot. There's a single envelope CFL with the UVA there, UVA 1, there's UVA 2, there's UVB, UVC. You'll notice the that's the one, okay. Right, the halogen is the one I was looking at. Yeah, halogen lamps are quite high in UV, the longer wavelength of UV, because they are an incandescent source. So that tail goes down quite far into the UV in a halogen lamp. So quite a lot of UVA, but not very much else. Okay, that's the kind of lab measurements. I'm very impressed with Leona and the amount of work she did. But we're very hard to please. I'm not always as nice as I seem. Sometimes I'm not like this. And I'll say, these are nice results, Leona, but what do they mean clinically? You know, what do we tell the public? What do we tell the patients? So this is where the actual patient testing comes in. And you saw this picture earlier, and you can see what we're trying to do here. And we've got this scoring regime because we've got a lot of experience in measuring redness. And they're very kind of clinical endpoints. But we've got people with very good eyes that can see these things quite nicely and quite clearly. So single envelope CFLs, we tested 200 individuals. 154 were actively photosensitive. So in other words, these are patients who have come to our department for testing. They've been referred to us. We get about 4 patients a week referred with a possible photosensitivity. Most of them turn out to be positive, I have to say, but sometimes they're not actively sensitive when we have them. So that's why you have to look into background history and so on. So really it's only the active photosensitive patients that would react, if anybody is going to react to these lights, because the rest are essentially normal. We had 32 positive responses. In other words, out of our 154 active photosensitive patients, 32 reacted to these CFLs. By reacting, we generally mean produce an erythema, which is redness of the skin. Now, what are the kind of patients that are top of the league? Well, this particular condition, chronic actinic dermatitis, we did our pilot study a few years ago, and we ran a little kind of model, and we predicted that this group were going to be the worst affected. They're exquisitely sensitive, small percentage of the population. It's a delayed type hypersensitivity reaction. They can be sensitive to UVB, UVA, and some are also sensitive to the visible. It tends to be, it's not exclusive, it tends to be a condition that comes on with age in gentlemen. In their 50s and 60s, they begin to get sensitive to light, in this particular condition, CAD. It's an absolute nightmare. Their world has changed completely. They cannot go out during the day unless they're heavily protected. And this is a sort of example. I think you can probably see how red and sort of crusty that skin is. It's very, very uncomfortable. The first report of this condition was about 15 to 20 years ago in a group. It was one of the London hospitals, and they had identified 8 patients, and at least half of them had attempted suicide, just because living with this sort of condition is absolutely dreadful. If you can't go outdoors unless you're heavily protected, it does affect your mental stability. This was a patient that came for testing. It's quite difficult to understand these without going through it all. 5 centimeters distance at 2.5 minutes of exposure. What happens is a standard routine is we'll expose someone to a light source and then test them 24 hours later to see what the minimum erythemal dose is. So after only 2.5 minutes, you can see, even where you're sitting, that is already red. You multiply that up on someone's skin, that is a bit of a sunburn they've got. And it's only 2.5 minutes in front of one of these lamps. If you can pull away to 20 centimeters, the redness is probably about 20 minutes, somewhere between these. So that becomes much, much safer. Now, this particular patient, this is at 30 minutes, CFL testing, 24 hours post-irradiation. I was looking to see the distance, and it's not written there. It may have been 5 centimeters, it may have been 20. I think it was 20 centimeters. This guy reacted so strongly. He lived in Birmingham in England, and all the way up, he had to have the blinds closed in the aircraft, and he was all covered as he came in for photo testing. It's hard to recognize what's going on here because it doesn't look like this. And that's because before the skin got red, it started to swell. So that's what we call edema, tissue swelling, and you can see it looks like a bruising reaction, which is a widespread sort of erythema well beyond the area of exposure. That is a photosensitive patient. That is a guy whose life has just gone off the rails, and the poor lad, his life is a misery. We showed him the different kinds of lamps. We gave him a few LEDs. We said, it's not the nicest kind of light, but there's no UV. Why don't you try them, take them away, and if they work, then you know what you're looking for. That's the sort of reaction which just ruins your life. This is another condition called solar urticaria, which is a bit like nettle rash, but you can see again, I think you can see there's a bit of swelling going on. There's not a very clear erythema with these patients, but you do get this swelling reaction. That was through the dermaguard, which means we're cutting out the UV. We have 1 or 2 patients who react to visible light. We can't blame the lamp. The lamp's function is to produce visible light. So what we're always very, very clear in saying, yep, you need light to see, otherwise you're going to bump into things. So a lamp that produces a reaction to light isn't a bad lamp, but a lamp that produces a reaction to UV, in our book, is a bad lamp, because the UV is not contributing to the usefulness of the lamp. This is an interesting condition, polymorphic light eruption, because it affects a large percentage of the European population. These other conditions I was talking about, which are very, very severe, only affect very small percentages of the population. But getting on for 20% of Europeans have this condition called PLE. And it's more prominent in the north of Europe than the south of Europe. So it's like the further away you get from the equator, the less sunlight, the more of these kind of reactions that we see. They're not terribly severe, but we thought it would be quite interesting just to test this group of patients as well, because of the large numbers of people that are affected. So yeah, we got reactions from PLEs, and we can then give advice accordingly. I'm just trying to remember what that's about. I think we'll skip that because it's getting quite complicated and it's getting into some of the details. This condition, Porphyria, you may have come across this. This was old King George, the maddening of King George, which was one of our old kings in England a long time ago. And it's reckoned he probably had Porphyria, which made him a little bit unstable. and the men only went out at night. And some of the vampire stories are thought to have originated from people who had light sensitivity, so they only went out at night. Now, it doesn't quite explain why they drank virgin's blood, but then that, you can't explain everything in one go. But that's the porphyrias, and they can be quite tricky because they can also be reactive to visible light as well as UV. We also did this test on healthy subjects, and we were rather surprised we got 2 positive responses out of our 20 normal healthy volunteers. So that was a little bit of a surprise. I think Leona has summarized these results somewhere soon. Otherwise, we're going to have trouble keeping it together. At the moment, the message is there's a lot of UV from some of these lamps, more from single envelope than double envelope, and a large percentage of our actively photosensitive patients react to the UV from those lamps, but a relatively small number of normal human volunteers react. We'll skip that. Yeah, this was just to show the difference between different lamps. So this is what we called our rogue lamp, which could produce erythema very easily, nothing through the dermaguard because it's only the UV. This is another lamp, which is apparently the same kind of lamp, but you can see no reaction at all. So the measurements that we're making in the physics lab, the calibration lab, are translating exactly through to the measurements we're getting in the clinic. And that's always nice. Whatever you do in the lab, say, what's the significance of this in real life? How does this affect patients? Can we test this on patients? And of course, in this case, we can. So we've got a one-to-one mapping between the results we're finding in the physics lab and the results we're getting in the clinic, which is rather nice. The question then is, okay, does double envelope lamps help? So far, our testing has been done on single envelope CFLs. We've shown how nasty they can be. Does double envelope help? So what we did was we took 11 of our patients who had tested on single envelope and retested them on double envelope. 8 were negative, 3 were positive with reduced responses. So we could see very clearly that going from single envelope in the same patient to double envelope would reduce the positive reactions quite significantly. For many patients, it would eliminate it completely, and for others, get it down to manageable proportion. What can we say about LEDs? We got 1 positive. This was a solar urticaria patient, but this, in fact, was positive not just to any UV that happened to be there, but to the visible light. And you can see that here. That's 30 minutes through the dermaguard. And I think you can probably see it's very similar to 30 minutes without the dermaguard. This is a patient who is sensitive to visible light, so no amount of UV protection is going to help them. So we did 100 patients. They were all negative, apart from the one that reacted to the visible light. We retested them with CFL, and of course we got positives to CFL. So we were able pretty convincingly to pin it down to, yep, CFL is bad, and the rest are not so bad. I think we'll skip that. That's just looking at a patient with different kinds of exposures. So we're almost finished, you'll be pleased to know. So can we draw any conclusions? Yep, we can say that CFLs emit UV, which can exacerbate, make worse these photosensitivities. We know, we have shown that double envelope CFLs have a lower can lower the UV risk. And we've also shown that LEDs provide an even safer alternative without any significant UV exposure risk. So why are we not all jumping onto LEDs? Well, interestingly enough, there are query health issues on the blue light component, mainly, well, in fact, almost entirely because of blue light sensitivity of the retina. So before we sort of say, yep, go way out and buy LEDs, you're safe to look at them, we just have to hold back a little bit just because of the blue light levels. But for our skin patients, LEDs would be fine. And they are, of course, costly, and my wife doesn't like them. I'd like to acknowledge Leona, who did an enormous amount of work here. Just to remind you again that you're all welcome to come over to Manchester. I know it's short notice, but do remember we've kept a session for late abstracts, and as far as I know, the last I heard, there's still space there. So you could get an abstract in quick. It's actually 2.5 days in May in Manchester. And as I mentioned the other day, just as an attraction, because I know you're a little bit short of good football in this country, the dinner will be in the home of Manchester United. So you can go and see kind of what it's like over in Europe, the kind of football that we play. It's a bit different from you do here, you know, but hell, well, that's it. So see you along in Manchester next month, hopefully. And that's me well and truly done. Thank you. Wait, Ron, you know the rule is that if you don't know the answer, you have to kind of leave it to the experts. I'm not an expert. You see, I just stand here and talk. So these guys, including yourself, in subsequent sessions will answer the question. Go on.
I'll address it to you, and then they can answer. So the relative risk for UV exposure, relative risk for UV exposure from sunlight versus room light.
Yeah.
It's probably much more risky to be outside than it is
for normal individuals. It would be, because in terms of your lifetime exposure, we've got some joint work with Frank de Kroel over in Netherlands, and I've got a PhD student working on that, relative risk between sunlight and exposure from CFLs. For most people, the relative risk, you're much riskier outside. So don't say, oh, sun's bad, let's go in and put the lights on. Yeah, you still get a bit of risk, but it's less. But remember, our patients, the photosensitive patients, they know about the sun. Yeah, even in Scotland, they know about the sun, and they know how to behave when they go out in the sun. And when we had a guy in who was a lawyer, and we were going through all this, giving me all the stuff, and he said, okay, I go into a restaurant and I have a meal. What do I know about these lights? So. Yes.
And the sensitive patients that you see, there are some drugs and medications that make you sensitive. Yeah. So when you have the patients come to you, have they checked off a list of all these things?
Yes. So a very, very extensive medical history. In fact, one of the things, incidentally, that we do in our department, we do photo testing for the pharmaceutical industry. Some of it's laboratory-based, but most of it's actually clinical, because anybody can do the laboratory stuff. So we'll get Johnson & Johnson, one of these companies will say, we have a drug, according to their lab 3T3 assay, it is potentially phototoxic. Before the FDA will allow us to use it, they have to do some clinical photo testing. So we test the drugs on human volunteers. We make sure that they're not on any. We've got a big list of drugs that we go through.
And last question, from a personal standpoint, since I'm blind, I use one of those reading lamps that has fluorescent, like a 5 fluorescent bulb in one. I suppose that's quite dangerous.
Oh, yeah, you don't want to read too much.
No, I don't want to read at all. But
no, it's amazing. I mean, once you start reading, you think, oh, no, look at all this stuff. Yeah, no, it's not. Do you go red or?
Well, I go red when I read, because my blood pressure goes up.
Blood pressure goes up. In actual fact, it's quite interesting, because historically, and I'm going back sort of 5, 6, 7 years, reading lamps started being produced with halogen lamps. Now, a halogen lamp's a tungsten lamp that's at a higher color temperature, and it's got a quartz envelope. So they actually did produce some UV, which some people were finding a bit irritating. But that's why now they'll either have a built-in filter or a little glass or plastic shield, something to cut out the UV. Doesn't seem to be a problem generally, but yeah, there's a lot of UV out there. Stay inside, put the lights out, close the windows, and you're safe. Watch TV. Yeah, you could. But don't read a book.
Let's thank you, Professor.
Thank you.